Hello and welcome back. Today we will discuss about this next part of the PLDs and memory lecture. Today we will discuss about programmable logic array, PLA, programmable ROM, PROM and FPGA. So what is programmable logic array? This PLA represents another type of programmable logic but with a slightly different architecture. Okay, so this PLA combines the characteristics of the PROM and the PAL. PAL we have already seen in the last lecture by providing both a programmable OR array and a programmable AND array. That is, in a PLA, both AND gates and OR gates have fuses. Both AND gates and OR gates, they have fuses at the inputs. A third set of fuses at the output inverters allows the output functions to be inverted if required. Okay, usually XOR gates are used for controlled inversion. So this feature makes it the most versatile of the among the three PLDs. However, it has some disadvantages because it has two sets of fuses and it is more difficult to manufacture, program and test it than a PROM and PAL. So here you can see the demonstration of the structure of a 3 input and 4 output PLA with every fusible link intact. Okay, like ROM, PLA can be mask programmable or field programmable. With a mask programmable PLA, the user must submit a PLA programming table to the manufacturer. Alright, so this table is used by the vendor to produce the user-made PLA that has the required internal paths between the inputs and your outputs. So the second type of PLA available is called the field programmable logic array or FPLA. The FPLA can be programmed by the user by means of the certain recommended procedures. Okay, and the FPLAs can be programmed with commercially available programmer units. All right, so here we will see how to implement a full adder using the programmable logic array. So full adder truth table, we all know 3 inputs A, B and carry input and output. We have sum and carry out. And once we know the truth table, we can easily find out the sum and the carry out expression using the Carnot map. From the sum, we have to see for these ones under this sum column, these ones are coming from which input combination. So for these, since this is a 3 input function, so we will have 8 cells. So in those respective cells, we have to put 1 and we will get the sum and carry out Carnot maps. Okay, so once we have obtained this sum and carry out Carnot maps, so here we have to draw the 3 inputs A, B and C in with their along with the true function and their complements by using the inverter. Okay, so sum, what is the first term? A bar, B bar, C in. So A bar we will put this fuse, then B bar we will put this fuse and C in we will put the fuse and it will go to the AND gate. What is the second term? A bar, B, C in bar. So A bar we will put the fuse, B we will put the fuse and C in bar we will put the fuse, it will go to the AND gate. What is the third term of the sum? A, B bar, C in bar. A we will put the fuse, B bar we will put the fuse, C in bar we will put the fuse and it will go to the AND gate. What is the fourth term? A, B, C in. So A we will put the fuse, B we will put the fuse and C in we will put the fuse and it will go to the AND gate. So this is my entire sum expression. So this entire line we have to put the fuse in the output side also, and this will be going to the sum. An OR gate, and the OR gate output will represent the sum. Similarly for carry also we have to give inputs to the AND gate and outputs also we have to put the fuse and it will go to the carrier OR gate. Okay, so these two OR gates are unused. This is how we can implement the full adder using the PLA. Now, what is programmable ROM or PROM? So, programmable ROM, it can be viewed as a type of the programmable logic array, and thus it can be used for that purpose. The address inputs to the PROM serve as logic variable inputs and the data output as the mode where the output of a logic function is realized. For example, stating that a 1 is stored at the address 1001 is the same as stating that the logic function being implemented equals 1 when the input combination is A, B bar, C bar, D. That's what A1001, right? So in both the cases, the output will be 1 when the input is 1001. When we regard a PROM as a PLA, we realize that the AND gates are not programmed. These AND gates are not programmed when we realize the PROM as PLA. Okay, and in effect, an AND gate is already in place for every possible combination of the inputs corresponding to every possible address of the PROM. So therefore, to program a PROM as a PLA, we must have the truth table that specifies the value of the function being implemented for every possible combination of the inputs. So for each combination where F is 1, we leave the output corresponding AND gate connected to the OR gate. So for each combination where F is 0, we burn open the connection to the OR gate. We see that the PROM is a PLD with a fixed AND gates and a programmable OR gates. And M by N PROM can be regarded as a PLA having N programmable OR gates capable of implementing n different logic functions of m variables. So this PROM ideally suited for implementing a logic function directly from a truth table. Now we will see how to implement a Boolean function using the PROM. Suppose 3 Boolean functions are given and they are expressed with respect to their minterms. Okay, so we have a 3 variable function, right? So we have to realize a function with a PROM with a size of 8 by 3. So an 8 by 3 PROM means a PROM with 8 address lines and 3 outputs. Since the PROM has 8 address lines, we have to use a decoder of size 3 by 8. That is a decoder with 3 input lines. Number of input lines k such that 8 to the power k means 2 cube. The number of output functions n is 3. Since the PROM has fixed AND gates, no minimization is required. Realization of the given functions using an 8 by 3 PROM is shown over here. The cross symbols at the crossover points of the grid indicate the connections. So to realize, if you want to realize these F1 address lines 047, they are connected to the output line F1. So it is a 3 by 8 decoder. So it will have 3 inputs and 8 outputs 0 to 7. So if you want to realize these F1 address lines, so 047. So this F1 means 0, 4 and 7. So they will be connected to the output line F1 and we have to represent it with the cross symbol. If you want to realize F2, that means 1, 3, 6, they will be 1, 3, 6. They will be connected to the output line F2 and we have to represent it with respect to this cross symbols. If you want to realize the F3 address lines 1, 2, 4 and 6, they are connected to the 1, 2, 4 and 6, they are connected to the output line F3. Now we will discuss about what is field programmable gate array. Okay, so we can, it says field means ability of the gate arrays to be programmed for a specific function by the user. And what is array? It indicates a series of columns and rows of gates that can be programmed by the end user. This is a larger and complex device. That means we can program the gate arrays and we can design the combinational or sequential logic circuits. Okay, suppose this first YOLO box is a PLD, okay, and this second YOLO box is also a PLD. So if we want to make a connection between them, we need what? We need this programmable interconnect. So this is the block diagram of your FPGA, where these blue boxes, they are the input output blocks. These lines are programmable interconnect, which forms the interconnection between these boxes. Okay, and these YOLO boxes are called the logic blocks. All right. Now, so suppose this yellow color PLD box, it is called the lookup table. Okay, so during PAL or PLA, PAL is programmable array logic and PLA is programmable logic array. So what we have discussed in PLA and PLA, we have discussed the AND OR configurations. Okay, so in FPGA, this AND OR is replaced by the memory device. Okay, now through this decoder, what we can do, using the min terms, we will get the logic function. So if we add all the YOLO box, if we add all these YOLO box lookup tables, then we will get the FPGA. Okay, now the decoder, what is the role of this decoder over here? This decoder, it acts as a digital switch or a selector. So it enables your FPGA to interpret the binary inputs and it activates a specific output line accordingly. All right. So what happens? It ultimately facilitates the memory access, data routing, and control signal generation within the PLD. Okay. So now moving on to this next slide. These logic blocks are basically programmable functional units, and what they do, they perform the computations. And these row and column interconnections, what are they? These row and column interconnections are the configurable routing pathways, and they are configurable routing pathways that connect these blocks horizontally and vertically. Okay, allowing the complex circuit analysis to be realized on the FPGA. Okay, and this diagram, it illustrates the internal structure of a logic element in an FPGA. So what happens? What does this mean? Suppose this lookup table, it has the 4 inputs. Okay, input A, B, C, and D. It is entering to your lookup table. So this lookup table, it performs the logic function based on its configuration. And these carry in signal, it can be used for arithmetic operations like additions. Okay, now the output of this lookup table can be fed into this cascade logic to chain multiple lookup tables, and it will allow the implementation of the larger function. So this cascade in signal, it allows this logic element to receive the cascading signals from a previous element. Okay, so these cascade out, the cascade out signal, what will do, this cascade out signal, it passes the combined or propagated logic to the next element in the chain. Now the output can be stored or manipulated via this flip-flop and control logic. Okay, which is controlled by this clock or preset or clear and the select signals. Okay, and if there is the carry out signal. So this carry out signal can be used for further arithmetic operations downstreams. So what are the advantages of the FPGA? It can do anything. It is super fast, field programmable, massively parallel, and high input output count. But it has some disadvantages too. It is expensive, it requires high power, volatile, it is having high pin count, complicated, many traps, complex tools. It is hard to choose or compare, and programming is not easy in this FPGA.